Okay. Next part is k-means clustering. You will see k-means clustering also used quite a bit. This general type of clustering is called a partitional clustering. If you think about hierarchical clustering, every gene belongs to not just one cluster, they belong to all the clusters above it. At the end, that's root cluster includes all the genes. Whereas partition clustering is a gene just belong to one cluster, but it would not belong to another cluster. In fact, you can create these type of partitional clustering from hierarchical clustering. Supposedly, we have expression data, and you have already clustered those genes based on their expression correlation across the samples. And you have this hierarchical clustering tree. And now I want to have a partition cluster of, say, 3 clusters. Or let's just start from 2. If I want to do 2, you can imagine I start from this hierarchical clustering tree. I just move my line a little bit lower. Initially, I have 1 cluster, and as I move lower, I'll have 2 clusters. Right? If you want to have 3, I keep moving onto here. There will be 1 cluster here, 1 cluster here, and another cluster there. And then I keep moving down. I'll get 4. It will be like 1, 2, 3, and 4. So in some sense, if you have a hierarchical clustering, you can create the k-means at whatever, not the k-means, you can create the disjoint clustering at whatever number you want to create, these disjoint groups. And once you create a disjoint group, for example, if I want to have a partition cluster of 4, this gene will only belong to this cluster, but it would not belong to the other ones anymore. Okay, that's why it's disjoint. The very popular approach people use is k-means clustering. So we are now showing each dot as 1 gene, and we're only showing you the expression of this gene in 2 samples. For example, the y-axis is this gene's expression in sample 1, and the x-axis is this gene's expression in sample 2. In reality, when you have 10 different samples, this will be a 10-dimensional space, but it's a little harder to draw. The algorithm will operate in the same way, but I want to only show you in a 2-dimensional clustering approach. So supposedly you have a number of genes and we measured their expression in just 2 samples. In multiple samples, it will be the same idea. For k-means clustering, we have to determine the k ahead of time. Let's just say we choose k equals to 3. In this case, we start by randomly choosing some centers. We say, we're going to have 3 clusters, and let's just randomly put some dots in here. And these are the initial center of the cluster. The next thing is, for each of the genes in my original data, I want to look at those 3 cluster centers and assign it to the cluster center that's closest to it. And so you can see these 2 points are assigned brown. And these points, even though they are pretty far, but they are still closer to this brown cluster than the green cluster. And and so on. So you assign each of the gene to its current closest cluster center. Next, based on the assignment, you calculate a new cluster center. So for example, now this new cluster center is based on the average of these 4 points. And these 3 dots will create the new cluster center in here. And these 2 are kind of outliers, but then you still use all the points that are assigned green to create a new cluster center. Then we iterate this process. We reassign, you can see, using the new cluster center, we reassign each of the points to the new cluster center. And so this point is probably, it's definitely closer to this. And this one, you can have to calculate whether it's closer to the red or closer to the brown. And also these 2 points, they have to compare with green versus brown. But you can imagine you do this iteratively. Every time you assign the nodes to its closest center and use that new assignment to create the new cluster center and then do the reassignment. You will finish when you end like this. All the the points are assigned and they are really close to their cluster center. And the next time you try to reassign the points, they don't change their membership. They're always assigned to the same cluster center. Then your iteration will finish. Okay? So that's k-means clustering. Of course, with a higher dimension data, it will take longer to calculate. So question is, if you were to start this algorithm a number of times, would they always give you the same result? No, it won't. So it's kind of a, it's a non-deterministic method. However, it's deterministic if your initial centers are set. Right. Once you pick the initial centers, there is only one way to get to the final clustering. But the initial center is important. And so depending on whether you assign the centers correctly, you might end up being getting something different. So we can see some cases. Just draw like this. So imagine you have a case where you have some dots, you say you have some cluster and you have this guy, which is really an outlier. And then you have some other cluster, and then you have, say, another cluster. But you say if you force this to be a 3, depending on how you start, maybe initially you pick those 3 correctly, these 3 will be okay. But if you initially pick this as your cluster center, then you might end up having a cluster that's really far away. Okay, so it really depends on how you start. So how do we really pick the initial cluster centers? You can imagine you start by running a hierarchical cluster, and then you find the line to cut to create a disjoint and use that as your initial k-means clustering center. And then you iterate until you converge. That's a possible way. Yeah, or you can randomly start many times with different centers and see which one give you the smallest within center distance and the biggest between cluster difference, right? But in general, k-means cluster is not as tolerant to outliers and noise. So in order to deal with this situation, let's look at the, oh, sorry. I'm trying to find my mouse. Okay. Now we're good. Yeah. So, yeah, okay. I guess I need to annotate and clear my tools. Then I can do this. Okay. So, yeah, this is exactly what we mean. When you have an outlier like this, depending on how you start, you might end up being something different. And also you can see this second cluster center is not very representative because of this single gene outlier. Yes, a question. You might end up getting a different result after you do k-means later. You can see that sometimes the membership would change. Either way is okay. I would think, depending on the biological question you want to answer, some people use hierarchical clustering, others will use k-means. As we mentioned, sometimes there are genes that could be outliers. And depending on how you start, your k-means cluster might end up being different. And also you see this case when the second cluster center is not a very representative location because of this one outlier gene. Right, so a way to get around that is instead of, and by the way, supposedly this point is extreme on the left. You might end up having a cluster center that's not even like most of the genes around here, but you get a cluster center around here, which is not what you want, right? And so one way to get rid of this outlier is to pick one real data point that's closest to all of the other point, instead of calculating an average as the new center of the cluster. So for example, in the previous assignment, we already have this, but instead of calculating a cluster center that was around here, we say out of the 4.1, 2, 3, 4, which is the point that's closest to the other three, and we pick this one instead of calculating this, which is further away from everybody. And in this red one is easier. Instead of the middle, you would just pick one that's closest. And usually it will give you a more robust result in the presence of noise and outliers. Another question people have is how to pick the number of k. You can imagine you start from k equals 2 and you gradually increase the k, because every time you increase the k, you have more clusters to manage. That will definitely reduce the within cluster distance, right? Any cluster that was previously, supposedly you have two clusters, you try to separate. Let's just say if we have data points like this, you try to do 2, and you say, okay, this cluster is still very noisy. Let's try to cut them into more clusters. Every time you add one number to the k, you can reduce the cluster within cluster distance. And you can also increase the between cluster distance. Therefore, the ideal case is we have k equals the number of genes in the array, but that's not ideal. So there is usually a cost, right? Your goal is to reduce the within cluster distance and increase the between cluster distance. But every time you add a k, you add a cost to it. So you will continue to add k if you can justify how much gain you get from the improvement. Okay, yeah, so you compare the cost with the improvement and stop it when it's not worth it, basically. That's the general idea. And so you can calculate the total sum of squares of distance within the cluster and also the sum of squares of between the cluster means, right? And supposedly n is your total number of data points or total number of genes in this case. In around 1974 and 1975, people have devised different approaches. The general goal is to say, yeah, we want to penalize, we don't want to go too high, but we realize every time you increase the k, it should reduce your within cluster distance and increase your between cluster distance. And you're just kind of trying to weight it. I guess different algorithms use a slightly different thing. And the example that was published was using this data set, and they're trying to pick the k. And so with the first algorithm, you try to pick, and then when you, there is the point, you stop. Okay, that's the cluster you pick. With the other method, it's like you're low, and then finally you have a best point and finish. Yeah, so there are some standard tools to do this. These kind of algorithms work well when you have a data very clean like this, but when you have a pretty noisy data, it may not work very well. And so the real practical consideration is first, for expression microarray, you very often only want to cluster genes if they show any variability across all the samples. And also, in a real k-means cluster, this could be tricky if you have like hundreds of conditions. Most of the time, when people are dealing with 5, 4 conditions, there is the magic of 7. People mentioned this before. If you give people 5 nodes and they ask them which one is higher or lower, they can do it. If you give them another 5 nodes, they can do it. But if you add the 10 together, even though the first 5 nodes are very high on the keyboard, the other 5 nodes are very low on the keyboard, it's very clear that they are different. But by the time you're dealing with 10 nodes, most people will get confused which one is higher or lower. So in some sense, human has this mental capability to deal with 7. If you have a k-means cluster over 7, very often, unless you have a meaning assigned to it, you say, these genes are on some pathways, or those genes are B cells, those genes are T cells or something. Most people, by the time they have like 10 clusters, they mentally think, oh, this cluster is that cluster. They're starting to mentally merge it, even if you give it a k of over 7. Very often, people also want to look at very tight clusters. So let's see, maybe I'll show you everything. So imagine you have a case like this. This is the original data, and you have a lot of these random stuff in here. In fact, with gene expression microarray, you might have some gene that's just crazy, right? Some bubbles on the microarray, or whatever reason you have noise. So the original algorithm that we mentioned before, they will break down. And so there is a way to say, you know, we just need to care about those tight clusters in here. The rest, it doesn't really matter, even if there's noise, even if they're outliers. And so the way to do this is you randomly sample, say, 70% of the original data or original genes. You don't consider all the genes. Just take 70% of the genes and you perform a k-means clustering of the sampled data. And use the clustered center. If you have the cluster center, you can look at the original data and assign each of the gene to its nearest center, right? And so you have a matrix to say, okay, which gene is assigned to which cluster. You create a co-membership matrix to say, okay, this time these two genes are in this same cluster. And then you repeat this. You randomly sample original data again with, say, 70% of the data. You do k-means clustering. You get the new k-means, the cluster center. And then you, based on the cluster center, you assign all the original gene to its nearest cluster center. And based on that, you ask which of those genes are in the same cluster. And so each time you calculate which two genes are in the same cluster, so you can fill this co-membership matrix. Supposedly we do this 100 times, and you ask, okay, this pair of genes, they are in the same cluster in 60 out of the 100 times. The other two genes, they are only in the same cluster 1 out of the 100 times, or so on. And so by the end, you just want to find the sets of genes that have the high co-membership with each other. And so that result is basically, it will just give you those clusters that are really tight and ignore all the rest. This is not forcing all the points to come into some cluster. You can leave out some really noisy data out, right? So yeah, it's more tolerant and it might give you more biologically robust clusters. Okay, so that's on k-means cluster. Questions? Yeah.
It seems like the type clustering method is like cheating because you choose the one that has the highest average co-membership by taking random samples of your original data. Is this like a standard method that people use?
For example, in a cancer cohort project, let's say different hospitals collected lung cancer samples and they send this to National Cancer Institute, and National Cancer Institute then send them to a genome center like the Broad Institute to do expression, now RNA-seq, right? And the goal is to see within lung cancer, are there some subtypes? Let's just say there's adenocarcinoma, there's a squamous lung carcinoma, there's a small cell lung cancer, and then there's some, like a few ones that you're just not sure what they belong to. It's one weird, and maybe there's a misdiagnosis or something. Those could be outliers, so your tight cluster can get rid of those. You want to just get those clusters that are well represented, samples look very similar. So it is, I think in real life, it's probably interesting. Okay.